Until now, we have seen gradient descent, which is batch gradient descent. We have applied this batch gradient descent for our linear regression problem, and we have also applied whenever we required this. We are taking the same linear regression example because we are much familiarized with the linear regression example by using the gradient descent, how we are finding the minimum of the cost function. And after getting the minimum of the cost function, we are taking the theta values, parameter values, and we are substituting those parameter values in the hypothesis to predict the output. But this batch gradient descent is using all training samples for every step. If I am taking a 10 crore training samples, if my training samples are 10 crore, then in the hypothesis you can observe here for each training sample we are using the hypothesis minus y, and for all 10 crore training samples we have to find the error. We are adding that error, and after that we are doing the average and we are multiplying with alpha. This is a computationally expensive process because for one step in this batch gradient descent process, we are using for one step 10 crore samples, and for like that we have to do the number of iterations for finding the minimum of the cost function. We have already discussed this in the linear regression. Now assume we are having some 30 crores training samples. So for each training sample we have to find the h of x, and we have to subtract the training sample from y. Means we have to subtract the hypothesis function for that particular training sample from the output y, and the error we have to find. Similarly, we are using the errors of the 30 crore samples, and we are summing up these 30 crore samples errors for every step. This is what our batch gradient descent is doing. But now when we are having large data set, this is computationally expensive. We have to look for an alternative, which is stochastic gradient descent. What is this stochastic gradient descent? This stochastic gradient descent, instead of taking 30 crores training samples for every step, it is considering only one training sample. That is surprising because until now we have known what is batch gradient descent, that is taking 30 crore training samples for every step, but this gradient descent, stochastic gradient descent, only taking one sample. So this is computationally very effective. How we are approaching with the one training sample for every step, we will discuss about this. First, we have to familiarize with the cost function for the stochastic gradient descent. If you see in deep, there is no difference between the cost function of the batch gradient descent and the stochastic gradient descent. The gradient descent equation for the batch gradient is 1 by 2m sigma is equal to 1 to m h of x minus y whole square. We are taking the same equation when there is 1 by m into sigma I is equal to 1 to m. We are taking that term as similar term, and h of x minus y whole square, 1 by 2 into h of x minus y whole square. We are calling this term, we are naming this term as cost of theta, because we are considering this for only one training sample for a particular step. We are also indicating x comma y for a particular training sample. So when we really substitute this value, then this cost function value will be equal to the batch gradient descent. Now how we are approaching this stochastic gradient descent? Because we are having the 30 crore training samples, we have to first shuffle the data set. Randomly we are shuffling. After shuffling randomly, we are taking one training sample. For that training sample, we are predicting the hypothesis h of x minus y. The error we are taking, based on this error, we are changing the theta. For only one training sample, we are changing the theta. So our first training, based on the first training sample, we have changed the parameter values theta. And after that, we are doing the second iteration. In the second iteration, with the new parameter value, with the new theta values which we have got by using the first training sample, we are performing this inner loop iteration, and theta values again changed. After that, we are performing the iteration for the third training sample, and similarly we are performing the iteration up to mth training sample. Means if we are using the 30 crore training samples, our inner loop iterations will be 30 crores. But you have to remember, for every step we are taking only one training sample. For every step we are taking one training sample, how it will look graphically, that we will observe. These are contour plots, as you know. To represent the three-dimensional diagram in the two dimension, we are using the contour plots. This is the contour plot for the batch gradient descent, which is going from starting from this step, and it is going to the center where we are finding the minimum value of the cost function for theta naught and theta 1. This is our stochastic gradient descent. We are starting here by taking one training example, and after that, sometimes it may increment, sometimes it may decrement, sometimes cost function may take the arbitrary value, finally it may reach or it may converge, but we may not give the guarantee that it will definitely reach the minimum value. It may not reach even the minimum value also after the 30 crores iterations, but we are satisfied with the approximated minimum value. Why we are satisfied? Because we are having the 30 crores training samples, and the batch gradient descent is taking for each step 30 crores training samples. Here in the stochastic gradient descent, for each step we are taking only one training sample. At least if we get the approximated minimum or near minimum value, it would be okay to us. So this is how we are proceeding in the stochastic gradient descent. In the inner loop, we are taking the same equation for the theta as we have taken or as we have considered in the batch gradient descent. But here, instead of considering the sigma, we have removed the sigma. You can remember in the batch gradient descent, we have used sigma is equal to 1 to m. We have summed up all errors for the all training samples we have taken, but here only considering one training sample, that's why we have removed the sigma. And we are doing this iteration, we are doing we are iterating by using the for loop from 1 to m training samples. And in the outer for loop, you can observe there is a repeat. So this process can be repeated 1 to 10 times. If we have 30 crore training samples, then there is no need to repeat. If we do this process only one time, that would be sufficient. If our training samples are 1 crore, then we may do the outer loop process 1 to 10 times based on our requirement. If we are feeling the theta values we are getting are not giving the minimum of the cost function, then we may repeat the same process. Remember, after completing the first iteration of outer loop, we have a very good theta values. With these theta values, we are going the second iteration. Means in the first iteration of the outer loop, we have iterated 30 crore times. In the second iteration, we are iterating 30 crore times. The only difference is after the first iteration of the outer loop is completed, means 30 crores inner iterations are completed, we are now having a very good theta values. So with these theta values, if we are doing the second time outer loop iteration, then it will give a very approximated minimum of the cost function, which is very useful for us to finding the theta naught and theta 1. Based on this, we can predict the output accurately. So this is how, when we are having a large data set, even though the cost function we are not getting, the cost function we are getting is not exactly the minimum what we have gotten what we have looked in the batch gradient descent. We may not be getting the same exact minimum, but we are getting the approximated minimum that will be sufficient to us. We have to remember, here we are dealing with the data of crores, some 30 crores data we are dealing. So we are happy even if we get the minimum approximated minimum value. That's how stochastic gradient descent is very effective when we are dealing with the data in the crores of training samples.